talked about class A amplifiers, in which even if there is no input signal, the transistor still draws current from the power supply, and this results in having class A amplifier lower efficiencies. Okay, the efficiency could be lower. For example, for a dual supply or a two battery, having two batteries for both positive and negative outputs, the efficiency was even less than 10% for a class A amplifier. So it's a very low efficiency. I mean, you can have, for example, you can use a common emitter configuration of a transistor to have a high gain, but again, you have a low efficiency for class A operations, right? However, here we have a better configuration, and these are more commonly referred to as push-pull amplifiers, and they consist of at least two transistors. Over here in this schematic, for example, you see there is a transistor Q1 and Q2. They're connected in series, and you also notice that the first transistor is an NPN transistor, okay, and the second transistor is a P and P transistor. So what happens is that if you have an AC input, right, and let's consider a positive cycle. This is the coupling capacitor C1. So for a positive cycle is coming at both ends. Okay, the bases of both transistors are tied together, and what happens is that Q1 turns on. Why it turns on? Because the base emitter junction is forward biased. Okay, and unless it's greater than 0.7, the transistor is it has to be greater than 0.7, so the transistor Q1 conducts. So for the positive half cycle, the transistor Q1 conducts. The transistor Q2 stays off. Okay, why it stays off? Because from emitter to base, the potential is it has to be greater than 0.7 again. Okay, I mean the base has to be at lower potential as compared to the emitter for PNP configuration. Okay, but this is not the case when you have a positive cycle. So the transistor Q2 is turned off, is fully off in the positive half cycle. So in the negative half cycle, when you have a negative half cycle, so when the negative half cycle comes, the transistor Q1 is off because base is at lower potential than emitter, so base emitter junction is reverse biased, so transistor Q1 does not conduct, okay, in the negative half cycle. So for the negative half cycle, you have a PNP transistor that conducts. Okay, so what happens is that one transistor is fully on in one part of the cycle, one half cycle, while the other transistor is off. So for example, when the positive cycle comes, Q1 is NPN, and it forward biases the base to emitter junction, and the Q1 transistor becomes fully on. Okay, while the lower transistor, which is the PNP configuration, is off. So it's like in the first half cycle, the Q1 transistor is going to push the current into the load, okay, as can be seen by the arrows. While in the other half cycle, the Q1 is off, but when Q2 is on, it will be like it's going to pull the current from the load. So the load is supplied with the load is being supplied with the full cycle, full 360-degree swing, and this 360-degree swing for half the cycle is being provided by one transistor. For example, for positive half cycle, it's Q1, which is pushing the current into the load, and on the load for the negative half cycle, Q2 is going to pull the current from the load, okay, down to the emitter side of PNP transistor. Okay, so one transistor is on while the other is off. So while one is conducting, the other is fully off. Okay, so that's the idea behind push-pull amplifier. So the two transistor push-pull configuration is as shown in this figure, and you also notice if there is no input signal, the both transistors are off. Okay, so transistors are not conducting for a full 360-degree of cycle, just like they're not getting supply from the DC batteries all the time. If there is no input signal, both the transistors are off, right? And if you have, because the base emitter junctions are reverse biased, so there is no conduction. Both the transistors are off. But if you apply an AC signal, then for the positive half cycle, one transistor is conducting and the other is not conducting. So when the positive cycle comes, the upper transistor conducts. So it's like the transistor Q1 is just taking the supply from the battery for the half cycle for 180 degrees. So this should give you an idea that the efficiency of a push-pull configuration, which is the power which is delivered to the load divided by the power, that is the transistor with the power drawn by the transistor from the DC battery, is not high enough as compared to Class A amplifier. It's not conducting for the entire cycle. So the efficiency of this configuration, push-pull configuration, is higher than Class A amplifiers. Okay, and this configuration is formally referred to as Class B amplifiers. Okay, their efficiency is high, and they can be used in audio applications where less harmonic content is required, or low distortion is required with high efficiency. So higher efficiency can be obtained from Class B configurations, and this is a push-pull configuration which is reflecting Class B. So the circuit provides the output voltage of both polarities and has a higher efficiency compared to Class A amplifier, because the transistor is not conducting for the entire cycle. So for example, in the positive cycle, Q1 is switched on, right? Q2 is like an open circuit, okay? And then in the negative half cycle, Q2 is conducting, is pulling the current from the load, while Q1 is an open circuit, right? So they are not drawing the current from the supply over the entire cycle, okay? So the top transistor allows the top supply to push the current into the load. The load transistor lets the supply pull the current from the load, okay? If you calculate the efficiency, it comes out to be 78%, which is much higher than Class A amplifier. Okay, this amplifier is still a linear amplifier. Why it's a linear amplifier? Because you can see since you're applying in this case you're applying a sinusoidal waveform at the input, and what you're getting at the output is still a sinusoidal waveform, right? So it is still giving you an output with a very low distortion, and the output is a waveform where the input it's the same form, it's the same waveform which is applied at the input, except that it gets amplified, or at least it is equal to what you had at the input. Okay, I mean, if you look at the configuration, this transistor is biased in a common collector configuration. Okay, so we don't have much of a gain in a common collector configuration. It's a little less than 1, so voltage gain is not high. In PNP transistor also, I mean, you see that the output is being taken from the load, but this is also a common collector configuration. Okay, so even if there is no gain, the output waveform is preserved. Okay, the output waveform does not contain any harmonic contents, harmonic frequencies of the fundamental, which is being applied at the input. Okay. But the efficiency is high, so they can last longer. I mean, the batteries can last longer for a typical push-pull configuration like this. So the efficiency is higher, 78% for a sine wave of maximum amplitude, since each transistor draws current from the battery over a half cycle only. So the transistors are not driving the current over 360 degrees like Class A amplifier. They're just drawing the current or power from the battery over a half cycle. Each transistor is driving the energy or the power from the battery over a half cycle. That's it. Okay. There are other configurations. So normally these push-pull amplifiers are normally set up to run as Class B amplifiers. They are referred to as Class B amplifiers in literature, which means that when the input voltage is 0, both transistors are just turned off and there is no power drawn from the supply. Okay. So this is different from Class A amplifiers. In Class A amplifiers, even if there is no input signal, the transistor is still driving the current from the power supply. Then this results in the lower efficiencies. Okay. However, in Class B amplifier, if there is no input signal, the transistor is off. So for low distortion, it is important that the crossover at I equal to 0 be continuous. So sometimes push-pull configurations amplifiers are run as Class AB amplifiers, which mean that each transistor is given some bias current. Okay, what does this mean is, well, there is one, it's not a pure sine wave that you're going to get. One of the disadvantages of this configuration is that what you're going to have is, for example, if this is your input, right? This is the input. The output is not a pure sine. The output. So if this is my input, Well, the output will have a distortion known as crossover distortion. So, okay, if it starts from here, okay, now this is the positive cycle, this is the negative cycle. So there won't be anything. There won't be anything unless the voltage level exceeds 0.7 volts. Okay, so let's say this is 0.7 volts. So unless the voltage level exceeds 0.7 volts, so there are two voltage levels, so we have to consider for both NPN and PNP. This is plus 0.7, let's say, and then we have minus 0.7. So in these, okay, so this is over here, this is again 0.7, so the output will be something like this. Okay, and then over here again, where this is cutting at minus 0.7, since PNP is conducting, so it's like this, and this trend continues. Okay, so what you are going to have at the output will be a waveform like this, and the regions where the current is not continuous, the load current is not continuous, is where you have this crossover distortion. Okay, so the class B amplifier is well, it is efficient, but it does produces these undesirable crossover distortions. It's not continuous at at I equal to 0 transition where there is no load current. Okay, so this is known as crossover distortion. So this problem can be alleviated if, for example, you can use diode or a battery. So, for example, if you are going to use a PN junction diode, well, you can also have the biasing resistor. Okay, you can have a biasing resistor, but this is going to reduce the efficiency of the circuit. It's not shown. So, but the idea is, again, the idea is if you have a PN junction like this, it's just like a battery. Okay, so you're going to have a battery of about 0.7, which is biasing the base at 0.7 volt. It's going to clamp this voltage at 0.7 volt, and it's going to make this base to emitter junction forward bias all the time by keeping this at 0.7 volts. It's applying the potential difference of 0.7 volts, which is the barrier potential of this base emitter junction. Again, over here, this is, you see that negative is connected like this. This is a battery, or you're having a diode like this. So 0.7, I mean, this base is at lower potential for a PNP transistor as compared to the emitter by 0.7 volts. So PNP transistor is always on. Okay, and this configuration, this particular configuration, is referred to as class AB amplifiers. Now, class AB amplifiers again have about the same efficiency, but they can alleviate or they can eliminate these crossover distortions, resulting in a good sine wave. Okay. You don't have any crossover distortion in class AB amplifiers, so you can use diode or biasing resistances or batteries like this. So you can use such configuration to always have the base emitter junction forward biased for both NPN and PNP complementary transistor configurations, so that you don't have any you have a continuous waveform. Okay, and you get rid of this crossover distortion problem. So, okay, this is another. It's not a complementary push-pull configuration. You see over here, well, you have and both the transistors are NPN. Okay, the problem over here is that the above transistor Q1, let's say, is in a common collector configuration. Okay, it's a common collector because the output is being taken from emitter, and the collector becomes ground. Okay, because you have to ignore this DC supply and AC signal model. So, but the lower transistor, this is not complementary, both are NPN. In complementary, you have NPN and PNP that we have discussed earlier, like this. So what is going on over here is in the lower transistor Q2 is in a common emitter configuration, right? It's a common emitter configuration. So if you recall, common emitter configuration and your basic electronics has a higher voltage gain, but it does produces phase reversal, right? And in a common collector configuration, the voltage gain is usually less than 1. It's used as a voltage buffer. But the impedance, input impedances are different. Okay, the output impedance of common collector is very low, but the input impedance is high. For common emitter, the input impedance is moderately higher. Okay, so you might require, first of all, different drive circuitry considering the input impedances of common collector configured transistor, and then you have a different ZCE which is the input impedance of a common emitter configured transistor. So first of all, the impedances are different, so drive circuitry requirements are different. The other thing is you cannot tie the bases together as we have. So, I mean, the base terminal was tied up together. This is one node to which the input was being supplied. What happens over here is you cannot tie up together, because if you're going to tie up them together, then if the positive cycle comes in phase, then both the transistors are on, right? So the efficiency drops. I mean, you can't have that. One of the transistors has to be off in order to be operate as a push-pull amplifier. So what you do is, for a lower drive circuitry, you have to drive this out of phase with respect to the upper transistor. So it has to be, the drive circuit should be such that if the positive cycle comes at a certain time, then at the same time the negative cycle should be there for the lower transistor. Okay, so the top transistor acts as an emitter follower. Again, this is a common collector. Why it's emitter follower? Because it's going to follow the input. So when it is conducting, because why it's a emitter follower is, I mean, you see whatever input voltage is there at the base. Okay, you have to subtract 0.7 from there, and then you have the output at the emitter, right? So it's just following the input. It's following the input. The output is 0.7 volts lower than the input. So whatever is available at the base or the input, just subtract 0.7, and the same thing is available at the output. So it's emitter follower. The emitter is following the input. Okay, so that's another name for common collector. So the top transistor is emitter follower. When it is conducting, the output voltage will be almost equal to the transistor's base voltage. Okay, so that's why it is emitter follower, and that's why I've said that the voltage gain is little less than 1. Okay, usually less than 1, usually 90%, something like that. So the bottom transistor, however, is driven in common emitter mode. Okay, so the bottom transistor is common emitter mode. So what happens is the two transistors need drive signals of opposite polarities, and they present different drive impedances requiring separate and different drive circuits. Okay, so more electronics is required with different drive circuits because the impedance is different. So this unappealing asymmetry is eliminated in complementary push-pull amplifier consisting of NPN and PNP pairs. So complementary pair is favored because you can tie up the bases together, and you can apply a single AC voltage or AC signal at the base, and one of the transistor will be conducting while the other transistor will be fully off. But at the load, we are going to have a fully conducting AC 360-degree cycle of a signal at the load. Okay, so apart from the crossover distortion, which can be eliminated if you can use diodes at the bases, so the base emitter junction for both the transistors is forward biased, so you don't have any crossover distortions. I mean, in class AB amplifier with the same efficiency, you can produce a low distortion or a pure sine wave as the output, right? So the complementary push-pull amplifier uses both an NPN and a PNP transistor. It uses an NPN and a complementary identical except for the polarity of PNP transistor. So it has both NPN and PNP transistors. This configuration is it still can work like for a push-pull configured for a push-pull amplifier as a push-pull amplifier, but this is not a complementary push-pull because it has both NPN transistors. Okay. All right. Now both operate as emitter followers. If you recall over here. Both of the configuration of Q1 and Q2, they are emitter followers, right? They're common collectors, so both configurations are CC, right? So except for 0.7 volt offsets, their bases could be tied together. This can be taken care of, as shown in figure, by using a pair of 0.7 volt batteries. In practice, this is done by some sort of a diode circuitry rather than batteries. So over here in this circuit, you see they are using batteries just to forward bias the base emitter junction of both NPN and PNP complementary pairs. So there is no crossover distortion. Okay, you have to forward bias the base emitter junctions. So that's why the batteries are here. So this circuit, in which both transistors are driven in common emitter mode, is found in some switching applications. So for example, one transistor is full on while the other is full off, and applications could be where low distortion, high efficiency, and high output power are required. Okay. For the calculation of efficiency, now let's again assume the maximum signal conditions, maximum swing conditions at the load. So we assume that VL, the output the amplitude is limited by the DC supply batteries which we have. So in the maximum swing condition at the frequency at which is being applied at the base, the output is the same. Okay, it's the same sinusoid, and the amplitude is limited by the battery supply VDC. Okay, so consider the top transistor which conducts during the positive half cycle, assuming negligible base current. The current through the transistor will be the same as the load current. So, for example, in the when the diode signal is such that a positive cycle comes, okay, so positive cycle is there, the upper transistor is conducting, right? So NPN transistor is on while PNP is off. So it's like pushing the current. This is an open circuit, right? You can think of it this as a switch. So the load transistor off, so this is going to push the current into the load, right? So the same current is going to flow in the transistor, which is being which is flowing in the load, right? So the load current under maximum signal conditions can be written as such. The load current is VDC cosine omega t by RL, right? Because this is the we are assuming the maximum signal condition. So this is the same current that is flowing in the transistor, okay? But mind that this current, this is the only positive half cycle for which the Q1 is conducting, right? It's not conducting for the negative half cycle, it won't, okay? It's going to conduct again when the positive cycle appears, right? So again, there won't be any conduction for Q1. So Q1 is not conducting for positive half cycles. Q2 is conducting for negative half cycles. So if you consider for Q1, let's take one transistor and average this out. I mean, if you take the average of the positive cycle only during the positive half cycle, the positive supply furnishes an average power which is given by, well, the average of VDC, which is coming from the positive supply, multiplied by the load current. This is load current, okay? And you multiply them, take the average. So this is VDC square into cosine omega t. So the average over positive half cycle is 2 by pi. So this average is 2 by pi, okay? It's not 0 because it's not a complete cycle, it's the half cycle. So you take the average over half cycle, it's 2 by pi VDC square over RL, okay? And then this is the average just over a positive loop. And if you understand, I mean, the negative supply, what happens when you have the negative part of the signal, the transistor becomes off, the upper transistor becomes off, while the lower transistor becomes on, okay? And it's going to furnish the same amount of power, because for the negative cycle, you're going to have the same average, right? So the negative supply during the negative half cycle is going to furnish the same average power. Since the circuit is symmetric, so the supply, the power that you're deriving from the positive supply, it's the same power that you're going to derive from the other battery. Okay, so the power that is obtained from the positive battery during the positive half cycle, the power that is driven by one transistor, Q1, let's say, is the same as the power derived from the other transistor, the lower transistor, PNP transistors. Okay, so it's the same. So if you consider for one transistor, I mean, in the negative half cycle, the NPN is off, and in the negative half cycle, PNP is on. So it's going to pull the current like this. This is the direction of the current. So the load current is again the same as the emitter current, right? And the load current is the same as emitter current, and the power drawn by the supply is the same as the NPN transistor. So the efficiency calculation is the same. You have to consider how much power is delivered to the load under maximum signal conditions. Under maximum signal conditions, you have to take the average. I mean, it's V square over RL. So you have to take the average like this. This is the power which is delivered to the load. And how much power is this? Well, that is equal to VDC square cosine square omega t divided by RL. Okay. So if you take the average, the cosine square term has the average of half. So this becomes equal to VDC square by 2RL. Okay. The average is half for a cosine square function. Similarly, it's half for a sine square function. And this is what it is. This is the power that is delivered to the load under maximum signal conditions, maximum swing conditions, limited by the DC supply. and the input power, the power that the transistor takes when it conducts for a half cycle, is 2 by pi. Since it's a half cycle, that's 2 by pi VDC square over RL. If you take the ratio, it comes out to be pi by 4, which is about 78.6%, which is much greater than class A amplifier efficiency. So you see, for a class AB amp, this is a class AB amplifier, which has the same efficiency as class B amplifier, but the advantage is that we don't have any crossover distortion. Okay, the output does not has any harmonic content. It's a faithful representation of the original drive signal. Okay, the drive signal is the frequency content is preserved. Okay, so where low distortion and high efficiency applications are desired, like audio applications, class AB or class B amplifiers are preferred. Okay, with high efficiency. So that's all for class B amplifiers. Thank you for watching.